Hello and welcome to Algebra 2, Chapter 7.2, and it's called Properties of Rational Exponents. So, two things to remember here. First of all, a rational number is a number that can be written as a fraction, so we're talking about exponents that are fractions. But the much more important thing to remember here is that we're talking about properties of exponents, and they have not changed since you first learned them. So these are the same properties we learned before. So here is your list of properties. This is the list from 6.1. It's also in 7.2. You should have them written down someplace. They have not changed, so I'm not going to go over them again. Okay, so we have used these properties before. We're going to make sure, though, this time to have them written down. These are probably the most important properties we can use when simplifying a radical. And the product property that says if you have a product under a radical that you can split it apart. Remember, this is what helps you to simplify a radical. So if you have the square root of 24, that splits up into the square root of 4 times 6, okay, which then is the square root of 4 times the square root of 6, and so that's how we get to square root of 6. The other one is your quotient property, and it works exactly the same, except you would have a fraction underneath, and this is what makes it really nice to square root, say, fractions, like the square root of 4/9 is the square root of 4 over the square root of 9, which is 2/3. Okay, so here we go. Simplify. So this first example, we are multiplying, and what do you do with your exponents when you're multiplying? You add them. So remember, you keep the base. Do not multiply the base or add the bases. You keep the base. And we want to add our exponents together. And so common denominator, that would be 3/6, and that would be 2/6. And so we add those together, we get 5/6. So it is 6 to the 5/6 power. Okay. So second example here. What happens when I have an exponent to an exponent? You multiply. So this becomes 27 to the 2/3 times 6 to the 1/2, because you get 2/4, which reduces to be a half. And then the question is, can you simplify this at all? Well, the second part is the square root of 6, which there's not a square root of 6, so you're good there. But this first part, remember, this would be the cube root of 27, and I'm going to put the squared outside. Cube root of 27, I'm going to use my calculator real quick just to make sure it is 3. So this is 3 squared, which is 9. So we're looking at 9 times 6 to the 1/2 power. Cannot do 9 times 6 because of your order of operations. So you just leave it 9 times 6 to the 1/2 power. Alright, so same thing here on the top one. I have exponent to an exponent. Okay. By the way, I'm going to do this one two different ways because there are two ways to do it. So the first thing is if you just say, okay, I have exponent to an exponent, so I'm going to multiply. So you're looking at 4 to the negative 1 times 2 to the negative 1, because 3 times negative 1/3 is negative 1. That moves both of these things to the bottom, and you would get 1/8 like that. Okay. Now the other way that actually might help you later on is that because they both have the same exponent, you can actually kind of factor out that exponent, and then the negative 1/3 would go past that, only because they have the same exponent. So then you're going to get 4 times 2 to the negative 1st, which is, you could have made it 8 to the negative 1st, which then ends up being 1/8. Okay, so something to keep in mind if they have the same exponent. And on our next one, we are dividing. And what do we do with our fractions when we divide? Not our fractions, but they are fractions. What do we do with our exponents when we divide? We subtract. So you keep your base, and then you have 1 minus 3/4, which would be 1/4, and you get 6 to the 1/4 power. Okay, so those all had exponents. These are going to be radicals. And the great thing about this is that you can change them to have exponents and then just change them back. So these first two here, following your product rule, because they're both cube roots, you can actually multiply what's underneath and you're going to get the cube root of 125. And the cube root of 125 is 5. All right. If you wanted to look at them as exponents, it would look something like that. And you can do what I just did on the last slide and pull out that 1/3, in which case you'd have 125 to the 1/3 power, which is 5. So there's lots of ways to look at these. All right, and the next one we're going to use our quotient rule. Because they both are cube roots, we can go ahead and just divide, and so we're going to have the cube root of 8, and we know that the cube root of 8 is 2. Okay, so just a little checklist so that if the directions say to simplify, that you know when you're done. You need to apply properties of radicals. You need to remove any perfect powers, okay, and that's the part of simplifying, like the square root of 24 we did earlier. There's that perfect power of 4 in there, so removing those and rationalizing the denominators. Remember we talked about that back in chapter 5. An easy one, if you have 1 over the square root of 2, you cannot have a square root of 2 on the bottom. You can't have any radical on the bottom. And so we would rationalize the denominator by multiplying it by what's going to cancel that denominator. Okay, so the directions say to write in simplest form. So 4th root is 64. So first thing I would do is I would check on my calculator, is there a 4th root of 64? Calculator says it's 2.828427125, and there's probably some more numbers to follow. So if there's not a perfect 4th root, you're going to need to split it apart like we have before with square roots. Now, because it's a 4th root, let's make a list of what are perfect 4th numbers. So 1 to the 4th power is 1, 2 to the 4th power is 16, 3 to the 4th power is 81, and you could keep going. 4 to the 4th power is 256. And the question is, are any of these numbers go into 64? Well, 16 does 4 times. So this is the 4th root of 16, sorry, and the 4th root of 4. 4th root of 16 is 2, so this is 2 4th root of 4. You're doing exactly what we did with square roots, except you just have a different list of numbers. By the way, while we're here, perfect thirds, 1 to the 3rd is 3rd, 2 to the 3rd is 8, 3 to the 3rd is 27, 4 to the 3rd is 64, 5 to the 3rd is 125. So these are lists that you can generate just by taking these numbers to their exponents. All right, so this next one here, if we use our quotient property, 4th root of 7 over the 4th root of 8, and there is no perfect 4th root of 8. Now, if I multiply by the 4th root of 8, I'm going to get the 4th root of 64, which doesn't do me any good either. So the question is, what number can I make 8 become that is a perfect 4th root? And so their answer is going to be 16. So if I multiply this by the 4th root of 2, okay, so here's the reason why. On the bottom, we now have the 4th root of 16. The 4th root of 16 is 2. And that really had nothing to do with this being a 2. That's just a 2 because I needed the 8 times 2 to be 16. So on the top, we have the 4th root of 14, which none of those numbers go into, and then that's your answer. Remember, no decimals. All right, so we can combine radicals as long as they have the same index and the same radicand. Remember, the radicand is the number underneath, and we combine them just like combining variables. So if I have a cube root of 3 plus 2 cube roots of 3, then I get 3 cube roots of 3. So just like they were variables. So if I have 5, 4 to the 3/4, and I subtract 3, 4 to the 3/4, how many do I have left? 2, 4 to the 3/4. Okay, just treat this right here just like a variable. I have 5 of them. I'm going to subtract 3 of them. I get 2 left. Now, that only worked because they were both 4 to the 3/4. So on this next one, they're not both 4 to the 3/4. So the first question is, can we simplify the cube root of 81 so that it's the cube root of 3? So 81 divided by 3, just because I'm aiming for 3 there, is 27. So the cube root of 27 times the cube root of 3 is 81. This is 3 cube root of 3 minus 1 cube root of 3, which happens to be 2 cube roots of 3. Okay, so simplify it so that they have the same radicand, and then do your operation. Okay. Now, when you're working with variables, because a variable can represent any number, lots of times you see answers written in absolute values. Because it does depend on whether the number is even or odd, the index, as to whether you would get a positive or negative answer. We, though, for the case of our class, we are going to assume that all of our variables are positive, and so we're not going to have to mess with that as much. But if you go on to college algebra, then you will have to take that into consideration. So I just wanted to let you know. All right, so simplify these expressions, and we're assuming our variables are positive. So I would think about this as the cube root of 27 and the cube root of z to the 9th. Okay, it's using your product property, separate it. Cube root of 27 is 3, so that's good. Over here, we're going to split this apart into the cube root of z cubed, the cube root of z cubed, and the cube root of z cubed, because I took those 9 z's and broke them apart into 3, 3, and 3. Well, what happens when you have a cube root and a cube? They cancel. So there's a z, there's a z, there's a z. Your answer is 3z cubed. Okay, so that cubed comes from the fact that you had 3 z's. So this next one, again, this is similar to taking the square root. Square root of 16 is 4. G to the, so we are multiplying because we're doing an exponent to an exponent, so g squared h to the first, and you are done. Okay, so same direction. So again, I would split this apart into the 4th root of 12, the 4th root of d to the 4th, the 4th root of e to the 9th, and the 4th root of f to the 14th. And there are no, let's see, 4th root, there are no perfect fourths that go into the 12th, so you're stuck with 4th root of 12. But if we look here, d, the 4th root of d to the 4th, well, that's just going to be d because those cancel. This next one, I'd make the 4th root of e to the 4th, the 4th root of e to the 4th, and we're going to have one more left because there's 8, we need one more to make 9. So there's an e, there's an e, there's a 4th root of e. And the last one, and so hopefully you've caught on, I'm making them in groups of 4 because they cancel with that 4th root. So there's 8, there's 12, and so how many do I have left? 2 more to make 16. So there's an F, there's an F, there's an F, and then I still have this 4th root. So the D came out, or I mean it's no longer under the 4th root. We had 2 E's, we had 3 F's, and then you get your 4th root of 12E F squared. So I would look at everything individually. Okay, so for this next one, I'm going to use my quotient property. make it the fifth root of g squared over the fifth root of h to the seventh. And for simplicity's sake, I would go ahead on the bottom and say this is h times the fifth root of h squared. And the reason is because we could do the fifth root of h to the fifth and the fifth root of h squared. Okay, because there's all 7 of them, so that totals there. And this one just becomes h. So now when you rationalize your denominator, all you're doing is getting rid of that h squared. Okay, but hold on one second, that actually needs to be a cubed, because for that to cancel, you have to have 5 h's underneath, and so I actually need to multiply it by h cubed. So this is going to be the fifth root of g squared h cubed over, so here's h, this is another h because you got the fifth root of h to the fifth, which is h, so you get h squared on the bottom. Okay, so 8 square root of x minus 3 square root of x is 5 square root of x. You are just combining those like terms there. Alright, so if I have 3gh to the 1/4 minus 6gh to the 1/4, that leaves me with negative 3gh to the 1/4. Alright, now this last one has an issue, because the first one we have the fourth root of 6x to the fifth, and the second one we have the fourth root of 6x. Okay, so they have to have the same radicand. So if we look at this though, if you just look at the fourth root of x to the fifth, that breaks apart into the fourth root of x to the fourth and the fourth root of x, right? Because there's all 5 x's accounted for. This first one comes out front as an x, so this is 2x, fourth root of 6x, plus x, fourth root of 6x. Or add those together, you're going to have 3x, fourth root of 6x. All right, so there's the 7-2 video. There is an extra one with more examples if you need them. We'll see you later.